Okay, my friends, you know I've been screaming about fission and fusion for years. We can do it with lasers using restrictive Venturis, and now the U.S. Energy Department is tapping into the same thing, calling it Frugal fusion. Before, they had gigantic, monstrous machines, and they never did even ever break even, I don't think. They claim now that they think they have broken even and maybe can get economical fusion devices. You're going to see we've already done it, and we can do this right now, I believe, and get exactly what they want is energy. Fusion is a nice word, but what they want is energy, and we can get that, I think, right now. So this is the BBC, nuclear fusion breakthrough. What is it and how does it work? Okay, my friends, all I can say is hang on to your neutrons, because we are about to talk about frugal fusion using lasers. Now, however, they're using heavy hydrogen. That I don't think is necessary. Heavy hydrogen is not necessary. It complicates everything, and the way they're doing it complicates way more than everything. Okay, we're going to take a look at nuclear fission in action in a moment, proving this statement to be correct. Nuclear fission is a reaction that occurs when nucleuses of atoms split into two or more smaller nuclei, releasing a large amount of energy. Energy is the white particles, so they go first. This process often produces gamma photons and neutrons that can trigger a chain reaction producing heat. First of all is the heat, just the heat, that's all it is, which is the radiation, and then the radioactive waste, which is the heavy particles. In a nuclear reactor, the water in the core is heated by nuclear fission, which is these particles hitting it, and then pumped into tubes to create steam. That's all it is. So nuclear fission is heating up the water and making steam to turn electric generators to produce electricity. So first of all, you have to have fissionable material that can do fission, and then you have to put it under pressure and all these kind of things to get it to create fission. It's not an easy thing, and it's dangerous because you're breaking up big things. You're throwing off chunks of things like this. All right, we're using particles of light, so we never get any bigger than a particle of light. This is us. But we still get the same product, which is this white radiation. That's the, excuse me, that's the particle that has all the energy. So let's see that particle in action. All right, I think this is going to be the easiest way. This is a little complicated, not bad. These are the particles they found at Fermilab and CERN. They say the smallest particles that exist, the muon neutrino, electron neutrino. Muon neutrino has this fuzzy, glowy edge around it, same color as its counterpart. Now, the two of them together make up what they call a Dirac neutrino. And one of them has all the mass, and the other one has no mass and has all the energy. It says in summary that black particles have a fixed size, but they have a fuzzy edge around them. The point-like particles are mathematical abstractions, zero size. They have no weight to them. That's why when you fill up a battery, it doesn't increase in any weight. They're mathematical abstractions, zero size. I can't explain it. It says that even the zero size particles have extended fields, and that's what gives them the energy. And that's these two particles. Now, did we find those? Yes, we did. And here they are actually attached together as photons. This is when they're in their stable state as photons, just floating around like normal. But we actually put them through the Venturi here with a red pulse laser, accelerated them through warp speed, and they exploded right at the Venturi and created fission here, and they came right back together instantly to create fusion. In the interim, if we could get right in there and harvest that energy, that's the white energy that drives a car. That is exactly what drives a car. It has no weight whatsoever to it. And I will show you this happening. And this one here, the Venturi was tuned in such a way as to only let a certain amount of black through. So it mostly was white. and here's the white leading the black. Now I'm going to show you an atomic bomb. What's going to happen in an atomic bomb is you have the bomb in the center, okay, right here. And there's a billion, zillion, trillion, gazillion times infinity number of particles around the black particles. All right, so the black ones are right in the center. All right, and these want to fall apart right now. They're just ready to fall apart. Now they pack all kinds of explosives around the outside of it, and they boom, they push it in, and then it goes out. Now what goes out first? Well, all the white particles. They're on the surface. Out they go. That's the white ones. They lead the black ones, which are here. So the white ones are taken off. Zip, they go flying. Every different direction, because in a nuclear bomb it's only one. We're going through the Venturi this way, so we can focus where we want to go. Now, and again, Rod Warren did this. This is all his work basically. I worked with him and worked closely with him for years. But he did the actual experimentation, and it was done. Anyway, we could talk about that later. Now, this is what they call Whistler waves. You see the distance in these waves? You see the distance in these waves? Why is that? It's fully understood. These are in the audible range, basically. You hear that kind of like a little rattle. And then this is what blows the house down. Now, let's see that actually happen. You see the house burn up, and just burn up, and all of a sudden the black hits it, and away the house goes. Okay, my friends, it's going to be exciting. This is the first direct detection of an electron neutrino at a particle collider. Electron neutrinos produced by proton-proton collisions at the Large Hadron Collider, CERN, have been experimentally observed. First time. This just came out a couple days ago, July 2024. Okay, my friends, hang on to your neutrons, because we are about to enter the realm of the subatomic. Now, I go into the subatomic, smaller than the protons, to the tiniest particles that exist, which are the neutrinos. Now, they are starting to use, it's called Frugal fusion. Now, this is from my good friend Pedro, who was with NASA and European Space Agency. He gets all of this stuff, and he just sent this to me. It just came out about this Frugal fusion using lasers instead of these huge particle colliders. But they're using heavy hydrogen. I don't think that's necessary. Let's talk about their process versus our process, because I believe we are also creating fusion. All right, we're creating fission here and fusion there. All right, when they come in, they come together as a black and white particle attached together, just like this. This is the colorized version of that. And when it hits the Venturi, the black separates from the white. That's fission. When they come back together over here, that's fusion. They come back together instantaneously almost. And you can see we're accelerating the light. I mean, there's so much that's wrong. But Fermilab sees the same exact identical particles. These are the same identical particles we see. Only we started with light. We started with the smallest particles. They started with huge particles. So they get just a big mess of collision of particle zoo, they call it. And these X particles could be any size whatsoever. So they don't realize it. But instead of a proton or a neutron being a big ball like that, it's a ball like this, composed of dipole electron particles. And when they crash into other dipole electron particles, which is another proton or neutron, they're all made of the same particles. And the only thing is, a neutron has one more or one less than a proton. They would normally say one more. So in other words, this right here is a proton. All right, it's a charged particle. It wants one more electron to become stable, or it wants to mate with somebody else and share electrons to become stable, because neutrality comes with an even number. So the neutron is an even number. I call it 1824. So this is a proton, 1823. Now it's 1824, it's a neutron. It's the only difference. Now when they collide these together, they end up with just enormous amounts of debris. And an X particle could be this big. It could be this big. It could be that big. So they've been searching for years and years and years, and now they've gotten to the point where they found what is the tiniest particles, and I too totally agree, is these are the two tiniest particles that exist. And attached together like this, they are what's called a gluon. We would have always called it an electron. A gluon means that you have a positive and a negative glued together. Back to back, it's like two-bar magnets, and then it becomes a photon. A gluon, which is an electron, wants to be attached to something. It wants to invade something. It's not happy being on its own. When these are back to back together, they create a field around them to say, we're good, stay away from us. We're good, we're light. And when it bounces back at you, and you can see it as light. And it depends on how fast it's coming and what it hits, and dependent upon, there's a lot of things that depend on what color light you're going to get back. And we can discuss all this stuff, because it's just nothing more than the frequency of the spin. And light spins, it doesn't flap like this, it spins in a circle. If you look at it from the side, in other words, there's light. If you look at it from the side, that's a wave. But if you look at it from the way it really is, it's a spinning particle. It spins like this. And the red is a real long spin. It's sort of slow spin. Green is somewhere around here. And blue is just like, and that blue will really whack you. Red is sort of a nice, easy, that's why we work with the red, because you can see the red much easier than you can see the green or the blue. Now, let's get in a little deeper, and I'm going to show you what they have to say about fission and fusion, and what I have to say about fission and fusion. And first of all, you have to understand the atomic model, which is not correct right now. The atomic model is the standard model, and it's just not right. This is really what a proton is. It's just like this. And in the center of all atoms, once you get to an atom, the black coagulates into the center. We never see it because it's deep inside. It's like this black ball right here. The black particles, they're individual particles, but they don't care. They can glob right onto each other. So they make a big ball in the center because the white ones want to be attached to them. They push them to the center. And at a certain point, which is apparently about 1823, they become stable. And you can't see inside to see the dark matter. Now, we see the dark matter because it sits on top of the white matter. And that's the only time you can see it, because it doesn't emit, it doesn't absorb, and it doesn't reflect. And I would say it's going to be absolute zero temperature in there. This is the stuff that has all the temperature. This is the stuff that has all the mass. And I don't think it has any temperature whatsoever. So I think this, if you could just isolate that and separate it on its own, it would be absolute zero, no energy. This is 100% energy, and I mean 100%. And when I say 100%, it has no weight whatsoever, but it is 100% of the energy. Can I prove that? Absolutely I can. When you charge a car, and it weighs 4,000 pounds, and it has no energy in it whatsoever, zero energy, 4,000 pounds, right on the money, 4,000. You charge that car up full charge, it still weighs right on the money, 4,000. Where'd the energy come from? Because now you could drive it 500 miles, no problem. Come back and everything's good, and now all of a sudden it's back down to zero again, but the car never changed weight. The energy has no weight whatsoever. And it's the white particles around here. This was hard to understand, but it is the energy. And then inside is where that dark matter is, just like that. The dark matter is pushed to the center and sucks all the energy towards it. The dark matter is what we call ground. Right? Ground attracts all your electrons. You take static electricity on your body and you get something like a water pipe, which is called ground. There it goes. Lightning builds up in the atmosphere. A lot of extra particles like this. Extra ones. They're just looking for a place to go. There's so many they can't take it anymore. To ground, which is the dark matter. Earth is saturated with dark matter. It's the ground. Now, this changes everything because the periodic table has to change. Not a whole lot. It's primarily that a hydrogen is not one big ball like this and one tiny, tiny little electron, and they both have the same charge. The electron and the proton have the same charge, but opposite. That's just, it's crazy. This is made out of all of these dipoles, and every dipole this is a dipole. Even though it's a ball magnet, it's a dipole. It has a positive and a negative, and when they all get together and they come together at a certain point, they get stable. And if you ever watch you know what I'm going to do? I'm going to show you the salt table experiments, because it shows vibration somehow sets up these patterns of stability. I can't account for that specifically, but it's about vibration. And the more of a vibration you get, the more exotic well, let's take a look. All right, here's what they have to say about electron neutrinos, and of course muon neutrinos and tau neutrinos. These are the three flavors. They're notoriously elusive, all right, because they don't interact normally. You don't see them, let me put it that way. And they say there are three flavors of these neutrinos. Now, they have found the muon and tau, they believe. Well, they have found the muon, that's for sure. And now they say that the first time they've ever seen the photon. First direct of an electron neutrino. But it's part of a photon. Here's the thing they don't understand. They think a proton is different than what it's made out of. It's not. A proton is made out of tiny little dipoles. And these tiny little dipoles make up light. Light is right here, and it is these neutrinos. There's a black one and a white one. They found the black ones before, the muons, but they never found the white ones. Well, we did, and I'll show you this in detail. Hold on. All right, if you want to look this thing up, they're talking about the FASER scientists inferred that there must be a parent electron neutrino in the detector from these cascades that they were seeing, and photons that envelop the trajectory of the daughter electrons. The daughter electrons, that's one that's given off just as an electron. So in this way, they found 4 electron neutrinos. Well, I'll show you what electron neutrino is. So here's what it is right here, electron neutrino. This is from CERN. This is from Large Hadron Collider. They say an electron neutrino comes in, and when it creates Cherenkov radiation, it turns into a shower. And the muon neutrino, the one they had found before already, the black ball, just continues on as what they call a sterile muon. They were attached together, called a Dirac neutrino. And here's what a Dirac neutrino looks like. Right there, a black and a white ball. And that's the same ones that we found, the black and the white balls. And we found them in all the 3 different colors. All right, here's the photons of red, the black and white balls. It's identical to what Fermilab is claiming. Exact same thing. And here's the, well, hold on, I'll get you the green. Hold on. Okay, so what is a neutrino? And what's the difference between an electron neutrino, which is the first they just detected forever, and a muon neutrino, which they detected a year or two ago. Now, electron neutrinos produced by a proton-proton collision, huge particles like this, bam, and they splashed them, everything went everywhere, and then they saw these electron neutrinos. Well, what is an electron neutrino? It is a white mass, a little white mass. Let me show you. All right, you could look this all up online. Fermilab long ago found this black particle, never changes size, has all the weight, and it has the glowy edge around it, which corresponds to the color of the particle that can get big and small and glowy. And we found those right here using light. So we didn't start with proton-proton, big huge colliders. We used light and funneled it into a very thin Venturi where it had to accelerate, and then it had to actually split. The black split from the white. So we can actually show the black on its own, and we can show the white in a spray. And then it comes back together with the black and creates a Higgs field. So this is what CERN and Fermilab and all of them saw, Lawrence, Livermore, Jefferson, boom. And I've communicated to all of them exactly what we found. So here's the particles. Now here they're attached together as a photon. So these two, which is a Dirac neutrino, which has the black and the white. One of them is actually an electron. We would always consider it an electron by itself. It does not want to be by itself. It's going to attach to something, it's going to burn into something, it's going to be heat. But when they're together like this in a dipole back-to-back bar magnet configuration, this is just that without the color. They just glue together. Now when they bounce off of something, they bounce off because they have a big magnetic field around them. Everything has a field, and when they're in this Dirac neutrino situation back-to-back, they become stable. Photons of light are stable. They go through the air all the time, just floating around. They're doing their thing, but they're bouncing, and then we're picking up the bounce. They're necessary to be stable, just like a proton. A proton has to be pretty stable because it's making up elements and it's making up matter. A light particle has to be stable because it has to keep going until it hits something, bounces back. It's a little complicated, but not much. And what we did was we took this light and accelerated that light using a Venturi, which is right here, and it's a very tiny restriction. So the light had to accelerate, and at that point the light actually pulled itself out of its own wave, exploded when it hit the Venturi, and created fission, where the black and the white separated, and fusion. Now, you can see the black particles right there. I'm going to get a better shot of this. But they call that the muon neutrinos. Are the black ones, they don't change. See the black ones, and they can't get through. The white ones go into the shower. It's virtually no question about it. And it's exactly what Fermilab posted as the two smallest particles they've ever found. This is just going to keep clicking up here. I'm down for a week, so that's just the way it works. All right, so they're saying that the first time they've ever seen the electron neutrino. They've seen the tau and the muon, apparently. I know they've seen the muon, the black ball. And they're all notoriously elusive. All right, they interact with ordinary matter only. All right, only with the weak force. That is absolutely not true. They are held together with the tightest of forces. Although you could say the weak force is the attraction of anything to everything else, if that's what you're considering a weak force. But they normally go with the weak nuclear force. There is no weak nuclear force. All right, interact with ordinary matter. Yes, I could go along with that. That's a weak force, but it does interact. And it can push its way in as heat. And it can evaporate out as heat. All right, so notwithstanding this difficulty, of finding these neutrinos. Neutrinos originated from astrophysical sources like the sun and supernova and from nuclear reactors, and fixed target experiments have been previously detected. In 2023, the Muon neutrinos, the black ball, produced by proton-proton collisions at a particle collider where, at a particle collider, previously detected at a particle collider, were directly detected by the forward search experimental FASER. That's where they smashed something through a whole bunch of stone, 500 meters of rock or something. All right, hold on a second. And that's the black ball. The black ball is just like hitting something against another. You know those how they drop those balls and they bang and a bang and a bang and a bang. If you had something solid enough and you hit those black balls against it, one would come out the other end. It's just like hitting here, and it goes flying off that side. Those Newton's cradle, they call it. Bang, 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 bang. They're coming through bang, and out the other end comes a proton. I mean a muon neutrino. So here's what they did. They previously detected in 2023 the muon neutrino produced by a proton-proton collision at a particle collider were directly detected by the forward search experiment FASER at the Large Hadron Collider at CERN in Switzerland. Now the FASER collaboration has reported the first direct detection of another flavor, the electron neutrino. And that's the electron neutrino. That's the muon neutrino. That's the electron neutrino. We found them. There they are right there. So it says the team used a detector made of tungsten. Now here's what they're trying to do. They want to work with protons. So they take a big plate of tungsten. They place 500 meters. So the team used a detector made of tungsten, placed 500 meters away from the point where the protons circulating around, and they smashed together here, and they were 500 meters away. That's like 1,500 or so feet. When the electron neutrino from a proton collision streams toward the detector and interacts with all right, let me try to explain this. When an electron neutrino from a proton collision streams towards the detector, which is this tungsten detector, it interacts with one of the tungsten atoms. It produces a highly energetic electron along with many other particles. So it just smashes the tungsten to bits, apparently. Now, the FASER scientists inferred the arrival of a parent electron neutrino in the detector from the characteristic cascade of secondary electron positron pairs. They're electron muon, actually, and photons that envelop the trajectory of the daughter electron. This is what they want, is the daughter electron. They want the energetic little part, the daughter electron. And that's how atoms are built. They're built with these little bitty particles. Basically this. They would see each one of these as an electron. It's not. It's a dipole. All right? And in this way they found 4 electron neutrinos. Now this is after years and years and years and billions and probably trillions of dollars. They found 4 electron neutrinos. Now let me show you what we did, because we found them too. Only we found lots of them. All right, so let's take a look at what we did. Now, what you have to understand is when they smash their protons together, they get brilliant, brilliant light, because they're sending out all these little bitty particles. They're smashing them to bits, and the little particles of light are flying off. But in addition to the little ones, the little light particles, the little tiny ones, they get chunks of big ones. X means they're just a chunk. It could be 100,000 pieces in there, who knows what. And all of these other ones are little bits and pieces of the proton-neutron collision. But primarily, you got a ton of light. Well, what is light made out of? Light is the protons. That's what we started with, was the light. We didn't need to start with proton-proton. This just is superfluous. You don't need to do that whatsoever. We started with light, so we shot light like this. Well, let me just show you how it all starts. Let's just take it from take it from the top. If I can find the top. Hold on, let me find the top. Okay, this pretty much explains light and the particles. This is a pulsed red laser. Now, it's just beginning to accelerate. Otherwise, we would not see these waves. There's a ton of waves in the air, but only this one is getting accelerated because it's going to be pulled into the Venturi. I'll show you that in a second. The reason you have all these little white dots all over is because these are gases in the air, moisture and so forth. And as this bumps into it, they have a field too. So they glow as this glows. The more push and the more impact, the more glow. Red doesn't glow a lot, but everybody's got to get out of the way, so there is a glow. Now, here it comes, and it's just starting to accelerate. Now here's where it really accelerates. It's actually pulling the particle, which I will show you in a second, out of the wave. And then it explodes here at the Venturi because it has no way to get. The only thing that can get through is the white, because the Venturi is so small that the black can't get through. So we're not a proton-proton collider, so they're correct. It's the first time it's ever been seen at a proton-proton collider. We see them in scads of them. But this is a photon accelerator. But it doesn't matter because all they have is photons too. You always end up getting down to the smallest bit and piece, and that's the muon electron neutrino. That's, as far as I determine, that's as small as they get. Now, coming through the Venturi out here, we can end up coming into these Higgs fields. And here's what they look like coming out of the Venturi. So this is going through this way. This is coming out at us. These are what the Higgs fields look like. All right, and they see these. They know that that's what they look like. But they just see them floating around here and there. Now, remember when I said there's many more fields here than this one light particle? There's a ton of particles coming, and here they are all here. You see that? There's one here. There's one here. There's one here. There's one here, and they were coming along with this. They're all in the air together. This is the only one dead nuts right through the Venturi. That's the one that picks up on the field. Now, why are these glowing? Because they're being pushed back against. This is an explosion. And when I'm talking about an explosion, I am talking about an explosion. That is a subatomic nuclear explosion. Subatomic, smaller than an atom. It exploded. And when it did, it created fission and fusion. Fission breaking apart here, fusion coming back together here. Now look at this. You see these fields here? That's reverse EMF, electromotive force. You see those backwards lines? They're not supposed to be there. They're there because of the explosion, the literal atomic explosion here, subatomic. And everything's brilliantly lit up. This whole thing, that is an enormous increase in energy from where it started here. Anytime you increase the luminosity, you increase energy. Have a physicist talk to me about this. If that's not true, I want to hear somebody say it's not true. All right, so this is the wave, which is the field, and the particle's back in here, but the field has to come through everybody else. Now all of a sudden the particle just ripped right out of there. It doesn't happen except for this Venturi. And the Venturi is so perfectly tuned that it only allows the white, which can shrink down. The black can't. Black is a fixed particle. Just look up point particle from Fermilab. They have exactly what it says. It's fixed. It cannot change. And that's exactly what we did find. And this is it right here from Fermilab. The black particle, that's it. It's the same size fits all. And has a little glowy part around it, which is the color of the glowy part. And that's exactly what we found. There it is right there. These are the particles. These are what we found. And the little one, I mean the white one or the glowy one, because they come, we found red, green, blue. I'll show you in a second. They can get small or they can get big. And here they get big when they hit. But then they squish right down and squirt through the little slit through here, this little Venturi. And that's because all of the fields are being forced into each other. All they're doing at CERN is hitting fields head on. But when you hit something head on, it's very easy for it to go this way, or go that way, or go this way, or go that way. And they do. They almost never hit head on. They get 25 collisions out of billions of particles, and they're thrilled. We got almost 99%. Or you could engineer this so that you'd have 100% collisions and be able to collect all of that energy. And I don't see any reason that shouldn't have excess energy when you create brilliance from almost no light at all. That is energy increase. Okay, so we went from basically darkness to total luminosity to luminosity on steroids and an explosion. And here's exactly what it says. Luminosity is an absolute measure of the radiant electromagnetic energy per unit time and is synonymous with the radiant power emitted by a light emitting object. So the power is increasing. More energy is here than was here. That means you should be able to get some free out of that. Okay, this is very important to understand. These are the two particles, the smallest particles that exist that they know of, which is the muon neutrino attached to the electron neutrino. They're both neutrinos. One of them has all the mass and never changes size, the muon, and one of them turns into showers, the electron neutrino. They've never found these before, they claim, but they have found a muon neutrino. Now, I claim that's what we have right here. The black ball is the muon neutrino, never changed size, it's all over the place here. The white, when it got restricted, it created showers. Now, I'm going to read to you what Cherenkov radiation is, because that's what they say. This is Cherenkov radiation. All right, and what is Cherenkov radiation? Well, here's how they explain it. Cherenkov radiation from a muon produced by a muon neutrino event yields a well-defined circular ring in their detector. It's just a black ball, which it does. It doesn't get big, it doesn't get small, same size every time. Now, what about the white ball, the electron shower? All right, Cherenkov radiation from the electron shower produced by an electron neutrino, which is the electron neutrino as it separates from the muon, produces multiple cones and therefore a diffuse ring in a detector array. Electron showers from an electron neutrino. We found this quite some time ago. And that's exactly what this is right there. The black ball is the muon, and the white turns into the showers. And the way we did it was putting it through a Venturi. And a Venturi is a very thin slit. It's rounded like this, and a very, very tiny orifice. And when the fields are big, the black balls are a certain size, never change size. See? The only reason you see these, that's dark matter too. And this also is gravity, which sucks the white back to it just voraciously. And the only reason you can see them is it's sitting on top of the white. You see them all over sitting on top of the white. As it fades out here, they're still all over the place, but they're just barely on top of the white. They're everywhere. The black balls are everywhere. And those are the muon neutrinos. And they recombine with the white particles out here and form the Higgs fields. When they come in, they're actually Higgs fields when they come in, and they're Higgs fields when they go out. And in the middle, they separate. See, remember, that's basically the Higgs field, if you ask me, heading in to the accelerator right here, the Venturi. And it gets sucked right out of there. Right about here, it concusses with its own backward push. Because back here, they're stacking up. Here, they're getting brighter and brighter because they're accelerating. And then all of a sudden, they're whacking into themselves back and back. So they think, right about here, they think they hit a wall. Same thing with these. This is what would happen when it hit the wall. It would be nice and bright. And that's what it's doing. It's making them bright because it thinks it hit a wall, just like here. And that's got to be an increase in energy. Now, don't forget, here they are out here. You see them, they're everywhere. I would call those Higgs fields. If these are Higgs fields, which they are, I would call those Higgs fields coming in and Higgs fields coming out. That's what I'm seeing. Okay, my friends, this just came out. First direct detection of electron neutrino at a particle collider. and this just came out July 11th, 2024. Now, they have been smashing these particles together for many years at the Large Hadron Collider, from proton-proton interaction, just bam, and they get all kinds of debris. And then they sort through it, and they have observed 4 of these particles. All right? Now, here's what they're talking about neutrinos. There's 3 flavors, they claim. There's electron, which is the white glowy particle. There's a muon, which is the black one, and I'll show you these. And then there's the tau, which apparently is right in the middle. Now, they're notoriously elusive as they interact with ordinary matter only. All right, they interact with ordinary matter only with the weak force. Now, there is a strong force. You see here that they're understanding now the landscape of particles is mapped like never before. Protons. They never expected the dipoles. My dipole electron flood theory, I know they're starting to pick up on this. Now, notwithstanding this difficulty, neutrinos originated from the sun and from supernova and nuclear reactors. Actually, no, they're attached to the black particle. Muons and electron neutrinos attached together. Everything came from somewhere, I don't know where, and it spews out of the sun, yes, absolutely. When we can divide these particles and break them apart and create muons and electron neutrinos apart from each other, I showed you, or I will. So they're saying that they did it by muon neutrinos produced by proton-proton collisions at a particle collider directly detected. All right, well, that's good. And this was at CERN. Now the FASER, which is this enormous device, collaboration reported the first direct detection of another flavor, the electron neutrino. All right, now they're going to talk about how they did it and da-da-da-da-da. I'm going to show you what they're looking for, the electron neutrino and the muon neutrino. And we found them. And here they are right here. All right, you see what, this is from CERN. That's not my thing here. Now, it's going to keep doing this disconnected. I'm offline. I'm going to be offline for a week. So, muon neutrino attached to an electron neutrino. That's the black and that's the white. And they shower apart when they hit a different field, you know, like heavy water for them. And the white turns into a shower, which it did. For us, we didn't have to do anything. We just accelerated it. So by accelerating it, it's exactly the same effect as pushing it through some medium that's restricting its flow, which is heavy water would say, oh, no, you're not coming through. Yes, I am. Boom. And it creates the showers. The same thing here. He says, this is too small. No, you can't come through. He said, well, we can come through because we can squish down. The black ones can't get through. And they just come as actually pulsed red laser slaps that through and showers those white particles through like unbelievable. And this could be addressed here. You could all kind of different Venturis, all kind of different pulse rates, all kinds of different frequencies, all kinds of different receivers. And I don't see any reason that we shouldn't be able to get something out of this. If it does actually, in fact, increase energy. And it appears to, because it shows low energy showers increasing up at a high energy as it comes through the Venturi, and the muons back off. Now this was, I can't remember who this was, but it was one of the big collider people, and they're talking about the electron neutrinos and the muon neutrinos, exactly what we have. And I see no reason we shouldn't be able to put this through the Venturi and collect it right here before it just collects back to itself, and then put it in some kind of little device like that. You put thousands and thousands and thousands of these. These are tiny, pinhead size, inside of a little lunchbox. And if you got more energy than you're putting in, you use some of it to keep going, and you got excess. That's what it sounds like to me. I could be wrong, but you know, that's just what it is. And I know they're looking at it because they're talking about new invention generates electricity out of thin air, offers clean energy 24/7. This was basically, I can't remember the article who put that out, but it's basically the same thing that I was showing. And here's the Higgs fields from CERN. And they're just big fields of blobs of stuff. Here's our fields. Look at this. These are the fields coming out at us. And they're all spinning. And the white comes out by itself and hits, it looks like, into some black ones, and they just start spinning. This one, it looks like spun backwards. And it's gathering the field into itself. And then it hit one of these and went crazy. I got some stunning stuff here. Look at this. This is the phone that took these pictures. Samsung Galaxy S3. And the other thing was a cheap Samsung little construction laser. That's what it was. This was a construction laser, and this phone took this picture coming out of the Venturi and showing the Higgs fields cascading at us. This one's being pinched. So the field itself has some form of an energetic value based on how big it is around or something, I don't know. And these are being pinched on the side, and it turned to blue because it's supposed to be red. They're all supposed to come through red. That one turned blue, and now it's phasing back into the red. By the time it gets out to here, it's red. But this bumped it forward, it looks like to me. I found that very interesting. This looks like to be the leading particle. There's nothing on either side of it. You see this? Check this out. This is coming through the Venturi. And there's nothing here. There is nothing there. So but the black particles are here. You just don't see them. They're not visible. However, you can see some of them. You see little black ones there trying to nibble into the white? And then you see down here, you see all the little tiny black ones. Can you see that? I'll tell you, this CMOS is absolutely amazing what you can see. Every pixel has its own amplifier. And they're designed strictly to see these frequencies of energy, which is, we call them light. And this, for some reason, this phone really was amazing. Now you see that little white zip? And then you see, it looks to me like it's hitting this field and it's creating that field. That's what I see. You see the little black particle, and then it's just, it doesn't keep going. The white particle, black particle, white. It starts to create that circle. And I see them here and there clearly, but most of the time not very clear. They just pop up. And they have to be there because there's nothing there. So everything appears to be saturated with black particles. Because there's no way in the world that I can think of that the black particles that were not allowed through here jumped ahead and got over to here to reattach. I can't see that happening. I think it's just there's a ton of extra black ones just waiting around to reattach to the white. I never thought it was possible, but in the subatomic realm, it is. They can divide apart, which I showed you, and I showed you the green. Well, maybe I didn't. Let's just look at it from the whole thing. Here's the green. You see that? That's a green photon. All right. That's the Dirac neutrino, and that's the muon electron neutrino. Muon neutrino, electron neutrino. Same thing here. And it's got a little spike because they spin coming through the air. As the leading one gains energy, it flops to the back. And I can show you that in the red. Now here's the red. Now the red is a little better. I can show you more about the red. The red is coming in from here. And remember I told you it's got to be exactly directly in line with the Venturi to accelerate. And this is it right here. You don't see any particles up here at all. Let me turn this light off. Maybe get a better shot. You see up there, there's no, you can almost see something going to happen here. Down below, there's virtually nothing. And then all of a sudden, you get a little bit of this. Well, these are neutrinos. They're not quite up to the photon phase. Photons are basically when you bang something and they're shooting back at you with a light. These are coming forward and they turn into a photon because they think they're hitting a wall. This is where that back field comes. Remember, I showed you that back field coming this way? That's why these are so brilliant here and turned into photons. Normally you don't get a photon, I don't think, until you actually concuss, and then you get it out. Normally you have these different values of neutrinos, and they all have the same thing. Like this is the red, and don't forget that's a neutrino. Now I don't know what the values of the energies are, but it looks like an Oreo cookie. And then over on this side, it almost is, you got white, black, white, black. This one here just has white in the middle, kind of big, and black on both sides. Why? I don't know. This is what a photon is. That's a photon. All right, and it's starting to be here, and here by here, it's a real glowy photon. Here, it explodes. It just breaks apart, and the white squirts through. All right, so that's what you're looking at as far as the particles go. It's just what it is. All right, this picture gives you a little more information. Remember I said one can get glowy and one can get real small, and that's why the small one can squirt through. This is it right here. This is light, and it's just exact identical particles, and they do exactly what they said at Fermilab. No difference whatsoever. Now, why is this one glowing? You see this one glowing more than that one? Why is that? You see these little particles here? Those are particles in the air, whether they're in moisture or in gases, whatever. Everything there is has a magnetic field because everything is made of these two particles. There's nothing that's not made of these. All right, and this is banging into them, and their fields are getting puffed up like this. So this gets puffed up bigger and bigger, and as it keeps going, it circles in a circle. This one comes forward with its weak energy, and it starts to absorb the energy and flows through. I don't think it's like sucking itself through the air. I think it's just flowing through the air and absorbing, and they will slow down. There's no question. I'll show you the blue slowing down. Light slows down and speeds up. You saw it speed up. If you can't see that speeding up, then you got a problem with you, not with me. I showed you this just a nice wave, and it was already starting to speed up, and now we're on steroids speeding up. And here we have division of the black from the white, and here it comes back together. It's all right in front of your face, and the only way to deny this is just to say, oh no, we're physicists and you're not. Well, I don't care who you are. This is what's happening, and this is what the case is. Now they come out through that Venturi towards us, and right here there's just nothing but white, and there's nothing there basically other than the energy, and all of a sudden they start manifesting into these fields. Now physics has it just about opposite. They say these fields break apart and give apart and break apart and form elementary particles. No, the elementary particles combine, which is this field. Now let me show you what this one did. I think I mentioned to you. I believe that one's spinning backwards. Let me scoot in on that. You can see, you see the trail it's leaving? It's twisted to the left there. I think that thing is gathering into itself, and it's spinning backwards. That's the only thing I can take from this, because it did concuss with one of the normal right-hand spinners. I think this is a left-hand spinner concussed with a right-hand spinner. Let me show you why I say that. All right, so now you look at this and you see, are these disks spinning, or are they just coming like a flat plate where there's no spin to them? I can show you they are spinning. All light spins in a circle. It's called the right-hand rule. If it's going that way, it spins to the right. So it goes here, and the field comes around this way. If it was coming this way, the field will go around that way. It's still the right-hand rule. Wherever the thumb goes, the field is towards the thumb. All right, so this is coming this way, the field is going that way. You see? That's the right-hand rule. Now, can I show that? Let's see if I can show you. I know I can. I will show you right now. All right, this is just way too cool. This is light spinning. That's what light does. It spins. It doesn't flap like a wave. All right, here's what the light does right here. There's the particle of light. It's a dipole. All right, it's four particles I showed you, the two blacks and the two whites. When it goes forward, it spins this way, and it spins, and it does spin this way. That's the right-hand rule. If it's going that way, it spins this way, you see? So it's spinning this way. Now, can you understand why it has this pattern if it spins this way? Don't forget, that's a field. When it concusses with something, it creates more energy. All right, so it gives it a little glow. But this is red. This is not very strong at all. This is the weakest of all the frequencies. So it doesn't give a big glow. But where you have in the center, you get a real good glow because you're forcing all of these fields to force through one tiny, tiny, tiny little orifice. That's the key. It's got to be tuned right. But these are all spinning this way. So just think about it this way. We're spinning, 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 spinning. Just come in tons of them. Most of them end up squirting right through the center. Now, why do you have this bump here and you have this bump here? And there's no real bump here and there's no real bump here. I can tell you exactly why. As this thing spins through the Venturi, there are actually two pins. It's smacking into the pin here, and then it dives over it, and then it smacks into the pin over here. But it's smacking here and gaining energy as it smacks into it, and then it loses energy. And then it gains energy as it smacks this way. So it is turning this way as it goes that way. It is turning. That's what light turns to the right. Now, remember that now. So we got light supposed to turn to the right, and all those fields do, and that's only one time I've seen it not do that. Okay, you remember our little friend right there. Well, what's he up to? He's going to smash into one of these. Now let's see if we can determine why this thing happened. You see that? This is that little particle, I believe, and I'm not 100% even sure of this, but I believe it is. These came to me, these batches of pictures at the same time. I would get these all the time from Rod Warren, who I've lost contact with. He did virtually all of ththese shots. Well, 90%, 99% probably. There was a couple other people, Fabian Boulay and I can't even remember some names. It's just, people just send me pictures. And this is what Rod did at first. And when I saw what he had, I knew what he was doing. And he very graciously worked with me. So I'm going to just leave it at that. And I would certainly love to hear back from him. But anyway, this is what happened. That little particle there, I believe. Let me turn this down so that maybe get a little bit better look at it. All right, let me come up really nice and snuggy. What are we looking at there? All right, we're looking at that particle coming just batched together. And then it hit with this particle down here, which is the normal right-hand spinner. So it's coming this direction. All right, so this is spinning this way. This one's spinning the other direction. Now, this is where it gets real interesting, because I believe, and I always thought, it must be the particle sits in the outside ring, and these are just fields emanating from that particle spinning. And I believe that's the case, and this indicates it to me. This one's coming this way. Now, if the particle is sitting in its outside ring, when it concussed with this particle and its outside ring particle coming this way, it stripped the particle right off. It just pulled it right away. And now it's heading off this direction. How it's going to end up, I don't know. But it was attached to this field. You can see, it's quite easy to understand. It was spinning this direction. And now it's being ripped off into this direction. You can see this, see the energy? This was a very energetic reaction between here and here. All right, and this, it's just stripped it off and spun it off this way. Where it goes from there, je ne sais pas, I do not know. You see this? This goes back about a year ago. Strange landscape of particles inside a proton, mapped like never before. Well, they're showing sort of like quarks and things like this. It's just not what it is. It's just entirely made of dipoles. And what happens is the dark part of the dipoles goes to the center and is surrounded by the white part. You see, there's the dark matter. It's in the center. Nobody's ever seen it before because it's in the center. Oops, we only work with atoms. You know, I work with light, so I can see it. But if you looked at that, you don't see any dark matter. There's no dark matter there. Until you break apart and smash apart the particles, then yes, you do see the dark matter. Dark matter is a muon. That's all it is. And it's also gravity. It sucks the white particles down to it with a vengeance. So it is in the center of all atoms. All right, when you get to the atomic level, I work in the subatomic. That is the atomic range. All right, I work in the particles that make up an atom. All right, atoms are made, one single proton is made out of 1,823 dipoles. So there's 1,823 black and whites. The black goes right to the center and the white coats it. That's what atoms are made like. That's why they've never seen the dark matter before. They just look at it. Well, now they have found it, and it's called the muons. But this is really what makes up a proton. There's 1,823 dipole electrons, and the black part is inside there. You just never see it. You can't see it until you break them apart. And then they have found it in the colliders, yes. But that's the only way you're going to see it. This is where they find it. And I think this was Jefferson. I can't remember. But these are the muons. These are the black balls. They can't get through. The white ones come through as showers. That's exactly what we did. Identical. Only we didn't use any heavy-duty particles. We just used light. So I think, I think this is important, that we should understand the reality of the situation, not just spend a whole bunch of money because, these people have some degree from somewhere. This is what actually, that's it. That's what the nature of light is. It's right in front of you. All right? They do see the same Higgs fields. Higgs, but they're huge, huge, huge globs of particles. They mean very, very little. Think about this. When this smashes, and this is just another one like this, boom, what happens? All right, the black particles don't emit light, they don't absorb light, they don't reflect light, they just go off on their own. And what happens to the rest of the stuff? It starts glowing. All right, the black particles are just there. Don't forget, dark matter does not emit, it doesn't. The way they found them, I believe, is because of the mass of them. I could be wrong about that. I can see them, and I showed them to you. But we also see these particles, which is the glowy ones. And I showed you the red, the green, and the blue. The blue, maybe I didn't show you the blue. Here's the blue coming through very, very fast. And then it's slowing down, and then you can see that there's actually two particles here. They all made it two dipoles back to back, which is light. And the blue, because you can see now, that was fast, now it's slowing down. So we know we can slow it down. And everybody knows that. That's not even in question, but nobody ever knew this, that you could speed it up. And we're not even in a vacuum. All right, they talk about a vacuum being in outer space. There's no vacuum in space. Space is saturated with particles and debris and dust and magnetic fields. And I can show you these. Absolutely, I can. So you say, well, then show them to me. Well, I'm glad you asked. Remember I told you that Rod Warren in Australia took all those pictures of the red stuff and all the photons and everything. This is his nephew, Dylan Carpenter, over in New Zealand. And he sent me a bunch of pictures, and that's the last I ever heard from him. And you can see space is absolutely saturated with fields. You plow through there, you're plowing through something that's going to restrict your motion. Red shift is not that everything's just being pulled away and light never slows down. No, light slows down. And I could think it can slow down pretty damn quick with all the stuff that's in space. Just look at that. Just think about that. Okay, so you have seen that we have created the muon neutrinos, and we have the electron showers, which are the electron neutrinos. Now, is this, and we have them in scads, I mean, you can't even count the number of them, and they end up, the white particles end up reattaching with the black particles to become a Higgs field, which I've shown you quite clearly. And here they are right here as they come back. Oops. as they come back together out here, they create these Higgs fields when they reassemble with the black. Now, is this meant to be deceptive? I don't know. First, direct detection of electron neutrinos at a particle collider. Now, they're colliding particles. We're forcing them through a Venturi. So that's technically correct. We have found the neutrinos, scads of them, long ago, in both flavors, the muon, the electron, and all the different neutrino values, the tau and so forth. Now, then they go on to make another statement that also sounds very tricky. Electron neutrinos produced by proton-proton collisions. We don't use protons. Proton-proton collisions, that's the Large Hadron Collider, have been experimentally observed. So that's also basically a true statement. But we use, in other words, they're using these big particles. I've shown you this very clearly, I know I have. And we're using the bits and pieces of these big particles, which is light. So they always end up getting light. When they smash it together, they get a lot of light, yes? We started with light. Why don't you start with the most basic first? Don't forget, trust me, they are extremely aware of my research. I went to the University of Geneva online for particle physics. I interacted with them. I showed them all my stuff long ago. And I said, I've got the particles you guys are looking for. And where we went back and forth because of CMOS, they didn't understand that you could see these particles. I said, no, you can't do it with a CMOS because it ruins the CMOS. But what they were doing was these big ones and hitting it with huge chunks. All right, where's my dark matter? Dark matter's already out of here, but they were hitting it with like a chunk like this. We never got even bigger than this. We never started with anything bigger than that, so we're never going to get bigger than this. And it's made to look at this. It's not made to look at these. They were right. You couldn't use CMOS in their configuration, but working with electrons, not working with protons, proton-proton collisions. No, we don't do that. We use the bits and pieces that protons are made of, which is the light, which is the two dipoles. All right, I can't go online. I got a serious issue going on for, it's going to be about a week. Now, you can go to dipoleelectronfloodtheory.com. Okay, dipoleelectronfloodtheory.com. All right, and that's, where is it? Right here. Dipoleelectronflood.com. I can't get into the internet. I'm down and out. It's going to be a week. All right, they say they found 7 tau neutrinos unmasked. The tau neutrinos are nothing more than chunks of protons. Okay, my friends, another shocker du jour, a nuclear fusion breakthrough. What is it and how does it work? U.S. scientists have reached a major milestone in attempts to perfect a process which could potentially deliver almost limitless supplies of energy. Now, I'm going to explain my take on this. They say, what is nuclear fusion? We're going to talk about this in a minute. All right, and this is what gives the sun its energy. That's not correct. Why is nuclear fusion so important? Well, we're going to talk about that. How does nuclear fusion work? Well, we're going to talk about that. And what is the products, and how does it start, and how does it end? What's released? What are the projects from the beginning till we get to the end? When will large-scale nuclear fusion be possible? Well, I say never. How safe is nuclear fusion? Well, we'll talk about that. Could nuclear fusion help tackle global warming? And then they're talking about how they give themselves on all their Nobel Prizes, and Einstein's work was wrong about black holes. Well, Einstein was wrong about everything. Light speeds up, light slows down. Everything is a disaster because of Einstein, literally. Okay, fusion's wonderful, but what's the goal? The goal is to replicate the process that occurs in stars where the intense heat fuses nuclei together to produce energy. So they think just the stars automatically create intense heat due to some gravitational forces to create these huge energy mass, and a corona and all this. So don't forget, this is what they want to do, is recreate the process that occurs in stars. Okay, I'm going to make you a physicist right now. 15 minutes tops. What is nuclear fusion? Well, here it is right here. It says it's the process that gives the sun its energy. Well, what is that process? In nuclear fusion, pairs of tiny particles called atoms, which are these protons and neutrons, make the atoms. They're heated so excessively and forced with so much pressure together, they make one heavier one. So they glob together, and instead of having two, they make one, and they give off a bunch of extra energy. Now they say that's what happens in nuclear fusion in the sun. All right, and then it says it is the opposite of nuclear fission, which means to split them apart, in which heavy atoms are split apart. We don't necessarily have to have heavy atoms. You can split actually light, which I'll show you in a second. Nuclear power stations currently use fission to generate electricity. Yeah, they're splitting apart the particles to make electricity. Let me show you what I have tried to present. Okay, my friends, this is going to be fun because I got that question from somebody the other day about Cherenkov radiation, which is right here. It's a radiation. It's a type of electromagnetic radiation. It can be seen near nuclear reactors in the heavy water. It's a radiation produced by nuclear fuel during fission. This radiation is a blue glow. Blue, remember this, a blue glow occurs when electrically charged particles like electrons or protons, and here it is right here, travel faster than the speed of light through a clear medium such as water or air. Same with what we did. The effect is similar to a sonic boom where the sound waves travel slower than the aircraft and form a shock front. Well, yes, that's true. However, Cherenkov radiation does more than that. It creates nuclear fission. All right, and it creates nuclear fission is the reaction that occurs when the nucleus of an atom splits. Now, they call about the nucleus of the atom. You don't have to split the nucleus. You can create nuclear fission of the light particles because they're part of the nucleus. So that's still nuclear fission when you break those, and we did this. All right, so we could break these little bits and pieces inside. We don't need atoms. So nuclear fission is a reaction that occurs when the particles inside the nucleus of an atom split into two or more smaller nuclei, which is eventually ends up being light, not nuclei, releasing a large amount of energy, which is light, is the energy. This process often produces gamma photons, which is light, and neutrons that can trigger a chain reaction producing heat, radiation, radioactive waste. That's because they're using gigantic particles like this. We're using single particles like these. These can't hurt you. This is like light. You're getting hit by these all the time. They may be pretty energetic, but they're only energetic for an instant. It's just like electricity. You get electricity on you all the time, static. It's not going to hurt you. The same with this stuff here. It's so instantaneously that it splits and comes back together, and there's such small particles. It's not like getting hit by a chunk of particle like that. That'll hurt you. Getting hit by one of these will just will brighten up your day. That's all. It's just a bright spot. So they pumped. Here's what happens. When they hit this the water with these high energy particles, because they're hitting them with chunks like this, and it's just smashing these other particles to bits and causing this blue radiation, which is here. You see the blue? The closest to the nucleus. And the blue takes off and creates that fission. So the radioactive waste in a nuclear reactor, the water in the core is heated by this nuclear fission, pumped into tubes to create steam. So they're making a steam engine out of this. It turns electrical generators to produce electricity. So they're calling that nuclear fission is making a steam engine to produce electricity. Yes, it's just making heat. All right, but a nuclear fission is the breakdown of big things into little things. And we did this with light. We broke down the light from big things into little things. All right, there's the light broken down here from the big thing, the black and white, into the little thing, the white. The black doesn't go through. And that is exactly what they call for right here. Where is it? Right here. Cherenkov radiation, just what I was talking about. The black particle goes on its own. The white particle turns into a shower. These are the neutrinos, muon electron neutrino. The white goes into the shower, the black goes on its own. And that's how what we did. We accelerated. It said they're going faster than they're supposed to go, exceeding the speed of light, like a sonic boom. There's nothing more. That's exactly it. And then they create havoc. And these particles separate. That's fission, and there's fusion on the other side. See the fission, the black and the white came apart. The black and white come back together. This is the only thing they're interested in, is this a white. This is the production of energy right here. This is electricity. And we separate it from the black. That's the whole idea of making electricity, is to separate the white from the black and keep the white over here in a bucket. It doesn't weigh anything at all, but you have to keep it separated and isolated from the black. Then you run it through the wires to get to the black, and it just goes zip. It doesn't care what's in front of it. It's going to push it out of the way. It makes motors run. It explodes body tissues. It heats water. It does anything to get to that black. So you got to get the white away, and sitting down here just waiting in your battery, which never gained any weight when you filled it up with the white. It never gained a single bit. And then when you go driving or doing whatever you're doing with that electricity, it's got to get to the black. So you can put it through heaters, you can put it through motors, you can put it through air conditioning. You can do anything you want with it. It's energy, and it has no weight. So you carry it around with you like it was nothing. And you could put these in a little lunchbox. I show this all the time. I can't see why you couldn't harvest that energy right there. That's all you want, is that white. That is the key to electricity, is the white. All right, there it is, frequency, Tesla. This is a plate hooked up to a vibrational, hertz. Every hertz is cycles per second. Now they're going to vibrate this plate. This is brush pulp. And at certain frequencies, it locks in a pattern. 345, you get this. All right, 1033, you get that. That's the rule of 8. 1820, you get this. I got to run it pretty fast, otherwise it goes pretty slow. And it just keeps getting more and more and more exotic as you get up. But you keep seeing this rule of 8 surrounding the core. It's got something to do with forcing the energy in and having it come back out against itself that creates these patterns. And they lock in at a certain, boom, 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 and they're just jiggling, and all of a sudden, boom, they lock in. And they get really, really exotic. Look at this. Look at these patterns out here. Now let me slow this down so that it's not way fast. Now let's come back here to where it starts out, how they just starting it out. All right, don't forget, the vibration is going to show up here, and all it is shaking back and forth the polarity of that plate. And the polarity of the plate forces these polar molecules, these salt molecules, to align in certain patterns. Now the first pattern is going to be what I would consider to be hydrogen or helium. Alright, so at 345, zzz, boop, it locks in. Now, dipole electron flood theory, there's not just one center and one particle out here somewhere. There's like 1,825 or so in the normal hydrogen 1. Now, they're all trying to get to the center. All right, now they maybe make this pattern and push all the dark matter to the center, because the dark matter will go to the center. All right, and that's the first line, and that's the only one that has only 4 in the outside orbitals, and they're tight. In other words, what you got here is you got the central black particles of the proton. It's all cored in the center. There's 1,823 of them. And all around outside is these little electrons. And they're organized, however they're organized, I don't know. But it looks like they could be organized in some pattern like that. But they're magnetic. And they want to get to this thing desperately. So they all get here. But now they push each other away because they don't like each other. They want to get to this. Now, these would be negative. They would not be dipoles. These would be just negative things, and they would not want to be next to each other. They would want to be out here, but all want to get to here, but all want to stay away from each other. If you can understand what I'm saying. So this is where all the black attracts to the center, and all of the blue attracts here, only in the hydrogen. Once you get up into the next levels, you have greens and reds and all that. But blue is the tight one. That's why when you see Cherenkov radiation, it says it's a blue emission, because you're going through water, which is H2O. And it's actually heavy water, deuterium and tritium probably in there too. But H2O, H2O. All right, so you got hydrogens all over the place. So that's why you're getting that blue, because that's what bounces off of here is blue, because it's so tightly held here. And when you hear a hydrogen explosion, it blows your eardrums right out of your head. A little tiny hydrogen balloon, and you hit it with a spark, there's oxygen and hydrogen in that balloon, it'll literally blow your eardrums out. So I'm not kidding you. All right, this gets a little tricky. Here's what he's doing. He's got H2O2 in this balloon. That's two gases. H2 is a gas and O2 is a gas. Now, and they're both gases in this balloon. Now he's going to hit it with a spark, which is an additional electron or electrons, which invade these little gases that are sort of hanging around freely now. Now, once they start to combust, this is fission, because everything's breaking apart. The H2O2 is breaking apart, and the O goes somewhere and it divides into electrons, it looks like to me, and the H2O comes out as like a water vapor. Watch what happens when he sets this thing off. Now, this is going to be loud. Wait till you hear this. The kids are going to freak out. Here goes.
If that sound was too loud for you, keep your mouth open, because then the pressure in your mouth will come outside here.
You see all the gases in the air? Primarily, that's water, because he had H2O2. Now you got H2O, which is water vapor, and the other O, I believe, turned into electron burst of energy. Just turned into raw energy. See, the kids. Now that's the way you teach. Okay, check this out. This is atomcentral.com, the Teapot Apple II Q House experiments, where they're checking out atomic bomb blasts. Now, they get all this set up, the truck is here, they're going to leave, the truck's going to go away. They set up all this equipment, and then they're going to set off the atomic bomb. Now, when they do, you watch what happens. Remember I said the white goes first. You'll see nothing but brilliant white. Now, there's going to be a hardened camera facing this way in a hardened closure. Now, boom, I'm stopping it. All you see is just brilliant white like this. Now everything's just smoking up. Nothing moved. Watch. This is running very slow motion. Nothing's moving at all. It's just smoke. You see the wires and the poles and everything back here? Anything that has any combustibility is just combusting. Watch the roof and everything. The whole facade of the house. The side is not being hit directly, so it doesn't combust. The metal tanks don't combust. But anything that is combustible combusts. Now watch, even the wires, all the wires, everything, and it's just a glow. Nothing has moved yet. Not a single thing has moved. They're just vaporizing. That is vapor. That's atomic vapor. And that is the white part of the atomic vapor. All right, so here comes the white part. Is all over here. It's just filling in because it has no weight, so it doesn't push anything. But it has to go out there. I don't know what it is. It's like some kind of a soap bubble or something. I don't know. And it invades everybody else's, and then everything just burns up and combusts. And then now here comes the black following right after it, and then the house will go. Don't remember the white came first, and now here comes the black. And away it goes. Watch it, everything's combusted. Boom, there it goes. Now, if they could tell the temperature right now of this exact instant when these particles hit, I bet you it's like way below zero. A dipole means you have the hotter, hot, and then you have cold. And that's what's happening in our atmosphere. Our atmosphere, or the scrub of our atmosphere into space, it's 3,000 degrees out there, and right underneath of it, it's minus 112 degrees. It's like 3,000 degrees difference in temperature between where that white was burning up here and the black over here. I would suspect if they could check the difference in temperature, we know the first part was just off the charts hot. I say this is off the charts cold. And that's what a dipole is. Now, everything will be sucked, it'll all get sucked back. And you can see it in other, where they show the trees going out and coming back. Watch it all turn around and come back. You see, it has to return to where it all came from, because now there's a void over here. All right, I'm pretty sure I talked about the atomic bomb blast. And here's the plutonium type. They claim they make the core of plutonium, which is very, very unstable, and they enrich it. They make it more unstable, and they put a ball of it in the center, and then they explode all these things into the same high explosive, and boom, everything goes. Remember I said the dark stuff is in the center, and all of the particles surrounding it are out here. So this is actually the dark core. All the particles surrounding it would be the blue particles, which are these energetic ones. So they're around that blue. Now all of a sudden they go, and they go boom, and it says no, and everything goes. Now that's implosion assembly method. This is the gun type where they shoot them down and they push two subcritical pieces together. This is uranium, this is plutonium, and they force them into such close proximity that they do the same thing as this basically, but not like that. That's much more powerful.